Hello everyone, in this video we're going to see binary index tree or Fenwick tree. So we're going to see the implementation, we're going to see how it can be used to solve several problems, and we're going to see one practice problem which can be easily solved by applying the concept of Fenwick tree. So I'm not going to focus on the theory part, but on the application, on the implementation, and see how it works, and we'll finally apply it in a problem, and so you get an idea of how this can be used for problems. So first, what is binary index tree, or what is it used for? So suppose we have an array. So I have 1, 4, 5, 2, 6, 3. Suppose I have this array. Now, I want to find the sum between a range. So sum range query. Sum range query meaning I want to find the sum between a range from L to R. So I want to find the sum of elements from L to R. So, and for different queries. So for Q queries, for Q times, so for Q times, I want to find the sum between L and R. So for first time, we have different L and R. For second time, we have different L and R. So for Q times, I have different L and different R, and I want to find the sum of elements from L to R for Q times. So so you can do this using brute force. Like for each Q, you can just run a loop from L to R and find the sum. But that won't be very efficient because that will have the time complexity as O of n into O of q into the sum of whatever the segment that is. So it won't be very efficient. So one method of doing this is using prefix sum array. So what does prefix sum array do? So I have just prefix sum array is basically the sum where ith number is the sum till that. So simple, I have 1. Now this will be this number plus the previous number 5. This will be this number plus the previous number 10. So this will be this number plus the previous number. I'll give some space so it's easier to understand. So this will be 12. This will be 18. This will be 21. Now, for each query, I can do this in constant time. How can I do this in constant time? Suppose after I found this, now suppose I want to find the sum from 3 to 5. So this is 1, this is 2, this is 3, this is 4, this is 5. So 3 to 5, you can see that the sum here. I want to find, this is the original array. So this is A, the original array, this is prefix sum array. I'll just write. So this is the prefix sum array, P. So this is my prefix sum array and this is the original array in which I have to find out the sum. So I want to find from 3 to 5. So without running a loop, let's first of all see what the answer is. So 3, 4, 5, the answer is 7 and 6, 13. So how are we going to find this without running a loop? So first let's look at the fifth element in our prefix sum array. So the fifth element is 1, 2, 3, 4, 5. This is 5. Now 5 minus the L minus 1. So L minus 1 is 2. So the element at 2, that is 5. So 18 minus 5, that will give us 13, which is the answer, which is from 3 to 5, 3, 4, 5, 5 to 7, 6, 13. So after we have made our prefix sum array, simply sum from L to R becomes a simple formula, which is a prefix of R minus prefix of L minus 1 from L to R. And if L is 0, then we can simply just say the answer is still that. So this becomes the formula for finding Q times the sum of elements from L to R. Very simple, and this can be done in constant time because why? This is just a simple formula. So the only time complexity is O of n, and O of n is when we run a loop to making the prefix element. So O of n for making the prefix sum array, and then constant time for finding the sum. For finding sum O of n. So you can see that prefix sum array is a very efficient way for sum range query. But what if we have updates? So sum range query with updates. So I have sum range query with updates. Now, what does that mean? That means that I have queue queries. So for queue times, I can have two things. I can either I want two things. I either want the sum L2R, or I want to update elements from say I want to update one element, update the element. So I can do two things. One, I want to get the sum from L to R. So I'll just write down one, I can get the sum from L to R. Or two, I update element at X by Y. Now what does that mean? So let's look at sum range query again. The sum range query is simple. For queue times, I can do only one thing. I want only one thing for queue times, that is sum of elements from L to R. Sum range query with updates is that I want the sum from L to R. For queue times, I can either get the sum from L to R, or I want to update the element at X by Y. So this means that suppose I have the same array, let's just get the same array. So suppose I have this array, and so suppose for the first query I want 3 to 5 like we had before. So we can just simply calculate 3 to 5 using prefix of 5 minus prefix of 2. So not a problem. Now in the next query I want to update the element at location 2 by 3. I want to add 3 to the element at 2. So the element at 2 is 4. So now this will become 7. So we will have to change our prefix sum array. So basically all the elements before it and all the elements after it will have to change. So that means that we'll have to update our prefix sum array. So whenever we're doing an update, it will take O of n time. So updating prefix sum array will be O of n. Now why will it be O of n? So suppose it was earlier 1 4 5 2 3, right? So suppose I want to update my prefix sum array. What was my prefix sum array? Let's just copy that again. So this was my prefix sum array earlier, right? Now this becomes 7 because I added 3 to it. So will I have to add 3 here also, 8. Uh, yeah. So I have to add here also 8, and then 5 plus 7, this will become this will also change. So I'll have to add 3 here also. So 13, I'll have to add 3 here also. So 15, I'll have to here add 3 here also. So 21, and here also. So 24. So meaning that everything after that element we have to update in our prefix sum array. So updating prefix sum array will be O of n. So again for queue queries. So for queue queries, again time complexity becomes O of q into like linear time. I'll say n for that. It won't be exactly n, but it will be linear time, q into linear time. So again, this is not very efficient, and so you can say this is not the very efficient, not the best way of doing it when we have updates also. So what do we do if we want to do this in a better method? Because now our now for finding, we can find in constant time. So 3 to 5 sum we can still find in constant time, but updating we have to do in linear time. So as I said, this is not the most efficient way. So what do we do for sum range query with updates? Damn it. Yeah. So what do we do for sum range query with updates? So this is where the Fenwick tree comes in. So Fenwick tree is something with where you can have two methods. So I'm not going into the theory part, we'll just see the implementation. So Fenwick tree has two functions. So you can have you have update and you have get sum. Now what is get sum? So in our prefix sum array, suppose like I said I want to find some, I'll just write here. So I want to find sum from L to R, sum from L to R. So with prefix sum array, This is simply a of r minus a of l minus 1, and this we can do in constant time, right? Because this is just a value and this is just a value, and we're just subtracting it and finding the answer. So what is a of r? A of r is sum till r, because this is prefix sum array. A of l minus 1 is equal to sum till l. So this is what it's doing. Get sum returns sum till a number. So if I have get sum in 10, it will return sum till n. And update is simply say index comma value. So this function, what this function will do is it will update the value at index to plus value. So simple. We wanted update some query with update, and that is what it's giving us. It's giving us sum till n. So we can use this for L to R. We can simply use this by how? Get sum R minus get sum L minus 1. So we can use this to find the sum, and we can use this function to do the update. So we'll get to the code soon, and we'll also see this problem. So now that out of the way, we'll get to the code, but what is the time complexity for this? So we were able to do this with prefix sum array also, but updation in prefix sum array took linear time. So in here, for Fenwick tree, updation and sum take O of log of n. So Fenwick tree, updation and sum take O of log of n. So you can see that it is better than our prefix sum array, because, well, log n is definitely better than n, like binary search is better than linear search. So this is where Fenwick tree comes in when we have some range query with updates. If we have simply some range queries, then we can make a prefix sum array and find the answer. So that's all. Now let's look at the question. The question is a practical implementation of Fenwick tree. It is just Fenwick tree. So this is the storyline. You can read it if you want to, nothing too interesting. So the formal description is we have an array which can contain element from 1000 to 2000. So we have an array. Three types of queries can be formed. We can add a given value to a single element on it, subtract a given value from a single element on it, and find the sum of the values between index I and j. So this is it. You can see that either we want to find the sum from I to j, or we add given value to an element or subtract a value from an element. And this is not just for sum, the updation. So if value is positive, then it will add that. If value is negative, then it will subtract that. So not a problem. So it takes the update. So this is what we have to do. We have to either update or we want to find the sum. So we have three characters. If s is given with I and j, we want to find the sum from I to j. If g is given, then we want to add this number to I. If t is given, then we want ith element. If g is given, we want to add this number to the ith element. If t is given, we want to add this number to the ith element. So very simple. This can be easily solved using Fenwick tree. So let's get to it. So we'll write the function update and get sum, and then we'll be able to solve it. So let's just do this. Type def unsigned int unsigned say long ull. So ull will be unsigned long, and constant int max is equal to 1 1 2 3 4 5 6. Okay. And ull a of max and tree of max is equal to 0. So binary tree is represented as an array. So you get to see this. Binary tree is represented as an array. So I'll just write the code. So this tree is our binary index tree. This tree is our Fenwick tree, and these are just variables. A is the array which will be given, which we have to update or find the sum from. So I'm declaring it before because we're only given one array and we have to make changes on that. So we don't have test cases, we have queries. So there's no problem if we make this global. So I'll just make the variables global, not a problem. So the variables used are n and q, the queries, and k, p, q. And we have a char m. According to char, we have to uh, update find the sum. Yeah. So we have the int main, and in int main what I'll do is I'll just take in the number of uh, elements and the queries, and then I'll just take in the array. So for int I is equal to 1, I less than equal to n, I plus plus. See in a of I, this is just taking the array, nothing. Now here is the main thing. Initially our tree is 0. You can see that initially it is 0. So you can see that I wrote two methods, which is update and get sum. So you can see, you can think of it as we have an array. So let's just take this array as the example because we have been using this. So the original array. So suppose I have this array. So if I have this array as my tree, meaning that if this array is the tree, then I can find sum from L to R using getSum, or I can make changes. But right now our tree is 0, 0, 0, 0, 0. So we have to make our tree as this. So how do we make our tree as this? Simple. The first element in the tree should be, I'll just copy this again. So we want this, we want to work with this array. So I want to work with this array, and initially our tree is this. So initially only we have to make this as our tree. So how will we do it? We want first on the first element. So we update the first element by 1. Simple. So this becomes 1. So this becomes 1. Now the element at second index, I want it to be 4. So I update this by 4. Quite simple. And then I can update this by 5, I can update this by 2, I can update this by 6, I can update this by 3. And by updation, you see that we have this, and then we can work on this. So my point is, tree is empty initially, so I want tree to be a of I. So how will I do it? I will say update I by a of I. So at the ith index, we have ai in our tree, meaning that our tree is now with a of I. Very simple. Now for each of the updates. So each of the queries. So we have cnm. So it says, and afterwards we have two elements, p and q. Now it says that, and also do remember that while working with Fenwick tree, index is, it's one based indexing. Indexing is one based, and in this problem it's given that array is 0 index. So I didn't take it as 0 index, I took it as 1 index, but in question they have taken it as 0 index. So I'll have to add 1 to both p and q. So I'll just add 1 to p here, and q will add afterwards. So if m is equal to t, then we have to subtract. Subtract meaning then just add minus q to it. We're not, p is the index, q is the value. So that is why we're not adding q, anything to q, because right now q can be the value. I'll just write it down. Q can be the value which is while updating, or q can be the index when p to q sum. So again in the question it is given that we have a character and then two numbers. So if the character is sum, then both numbers are index. We have to find the sum from I to j. But if it is g, then only the first number is the index, second number is a value. So we don't want to change the value. We want to exactly add this value. And if it is t, then the first number is the index and the second number is the value. So we want to add this value, meaning we want to subtract this value from the number at this index. So here, so if p is index, p is definitely index, so we added p 1 to it. If q is index, we have to add 1 to it because we have to take one base indexing. But if it is value, we can just leave it p. So if m is equal to t, then q is a value. So we can just simply say update the element at p by minus q. Why? Because we want to subtract q from it. So subtracting q is equal to adding minus q. Now else if m is equal to g. So again we have to update and we have to add. So update p and q. So we have to add q at the element at p. And else, now this is the point where we have to find sum from p to q. So p and q are both index. So I have already added 1 to p and now I have to add 1 to q, as we are using one based indexing. So q plus plus. Now if p not equal to 1, then I say res is equal to get sum q. Like I said, from p to q will be from L to R is get sum of R minus get sum of L minus 1. So get sum of q minus get sum yeah, we haven't written the functions now, we'll get to it. So get sum p minus 1, and else it is just till q, like I said. So get sum till q, and we just see out this and log. So you can see that we use get sum to find the sum from range, and we use the function update to find the update, but we haven't actually written it, so we'll just write the function. So let's write the function update. So void update, and I'll also give a link to my code in the description, you can check it out. And so update, we want to update the element at p by q. So while p less than equal to n, tree of p plus equal to q, and then p is equal to p and minus p. P plus is equal to. So with this, we'll update the value in log of n, and then ul gets sum and sum till n. So ull r is equal to 0, and while n greater than 0, then r plus is equal to tree of n. N is equal to n and minus n. N minus is equal to, we're subtracting n, we're going backwards, return r. So this get sum gives sum till n in O of log of n, and this updates the value in O of log of n. So we did our update, we did our sum, and with that we got the answer. And this is for each of the queries. Now let's just try to run it. This should be capital, we'll just make it capital. Okay, and this should also be capital. I'll just try it on the test case. And we'll try to submit it. copy everything. So it's taking some time. Yeah, so we're getting correct answer with this, and I'll just give a link to my code, and this is just, you can think of this answer or this code as the proper template for Fenwick tree. So that is how it works. I didn't cover any of the theory, like how it works. I didn't cover that, but I just wanted to tell the basic implementation so you can get to implementing it and solving problems with it. I'll give a link to my code, and I'll also give link to some problems which can be done using Fenwick tree. So that's all. Thank you.